In the next 3 lessons we're going to look at the uses of nuclear radiation. In this lesson we're going to look at some industrial uses. In the next lesson we're going to look at some medical uses, and finally we're going to look at the use of nuclear radiation for radioactive dating. So our first example of an industrial use is in industrial traces. For example, finding either leaks or blockages in underground tubing or piping. So imagine that this is a drain system which is carrying water and there's a leak in it. So in this case we've got a leak, but it could also apply to a blockage as well. Alright, so for leaks or blockages, and we want to find out where the leak is, so we introduce a radioactive isotope. Now the choice of radioactive isotope in all of these applications is important. So you've got to consider exactly what type of radiation you want to be emitted. And in this case what we need is gamma radiation, because the radiation's got to pass through quite a large distance, of solid material. Alright, so we're going to want gamma radiation. And the other important decision with regard to the radioactive source is the half-life of the source. So in this particular case you don't want a radioactive source with a really short half-life, one that's going to disappear within minutes or even less than an hour, because these industrial jobs can take quite a while to set up, and you may have to examine quite a large area of tubing. On the other hand, you don't want a radioactive source which will hang around for a long period of time, particularly where there may be a danger of people being exposed to radiation. So in this particular case, a very useful radioactive isotope is sodium-24. This has a half-life of about 15 hours. It's a beta emitter, but it also emits gamma radiation. So we can write the equation. That's going to give us magnesium. Remember, when a beta emission takes place, we move up one place in the periodic table, plus our beta particle, which is a high energy electron, 0 mass and -1 atomic number, and plus the all-important gamma radiation. And so the inspector just needs to move the Geiger counter along this pipe, along the tubing, until it starts to show an increase in reading. And when that happens, they will know that they have found the leak. Now the second use we're going to look at is that of smoke alarms. So here we've got a very simplified smoke alarm system. We have 2 electrodes, right, a negative and a positive plate, and in the circuit we have a detector, and here we have an alpha source. So the alpha source produces alpha particles. These pass between the plates and they cause the air molecules between the plates to become ionized. Right, so in between here we're going to have ionization occurring, and so we remember that we can't use beta or gamma radiation in this particular case, because beta and gamma radiation is very weakly ionizing through air, so there may be some ionization but very, very little. The only option in this particular case is to use alpha particles, which can only penetrate a small distance in air because they are quite strongly ionizing. And so when these particles become ionized, the positive ions will move towards the negative electrode. The negative ions will move towards the positive electrode, and as a result of that you will get a small current generated in the circuit. So what is important in smoke alarms is this current is constant. So not only do we require the radioactive source to produce alpha particles, but the source must also have a very long half-life. That's to say, what you want is that the emission of alpha particles is very constant, very regular over long periods of time. This means that the amount of ionization will be constant, which means that the current flowing in the circuit will be constant over long periods. So a radioactive source which suits this bill is americium-241. Okay, so we're going to use americium. That's an alpha source that has a half-life of 432 years. So that means you're going to have a very constant flow of alpha particles here passing between the plates. You're going to get a very constant current, and what happens next is that when there's a fire, then smoke particles will pass between the plates, and these will absorb the alpha radiation. Let's just carry on here. So the smoke particles will absorb the alpha particles. That will cause a drop in ionization, which will cause a drop in this current that's flowing around the circuit. Okay, the detector will detect the change in current and it will set off the alarm. Okay, so just to finish this, let's just write out the nuclear equation for the decay of americium. Okay, so we're going to have americium 24195. That decays into neptunium plus an alpha particle, which is a helium nucleus with nucleon number 4, atomic number 2. Do the sums. We take 4 from that, that gives us 237, and 2 from 95 gives us 93. Now then, the final application we're going to look at is in the measuring of thicknesses of metals. In this case, we're going to look at the control process for the production of aluminium foil. First of all, let's just describe this circuit. We've got the rollers here. These are pressing out the aluminium foil. Okay, so the thickness between these rollers can be adjusted so that we can change the thickness of the foil that's being produced. Now, this is our radioactive source. This needs to produce radiation that will be both transmitted and absorbed by the aluminium foil. Okay, and the only radiation that will do that is beta radiation, so it has to be a beta source. Alpha particles will be completely absorbed by the aluminium foil. Gamma sources will just transmit straight through it. So we have a detector here, and what we want is that the source has, again, a very long half-life. So we want the source to be producing a constant, regular emission of beta particles. We don't want that to change, so you don't want a short half-life there. So what's happening here is that as the foil passes through the rollers, if it, for example, begins to get too thick, what will happen is that more beta particles will start to get absorbed. The detector will notice that, and a feedback control system will tell the rollers to move closer together so that the thickness of the aluminium foil decreases. Now, if the thickness of the aluminium foil becomes too thin, then what will happen is that the detector will notice an increase in particles that are transmitted through the foil. It will then tell the feedback control system, which will then tell the rollers to move further apart so that the foil becomes slightly thicker. Okay, now the candidate which satisfies these requirements, a beta source and a long half-life, is strontium 90. Okay, and strontium 90 has a half-life of about 29 years. So that guarantees that during the daily operation of this machinery, or even the monthly operation, then the flow of beta particles from the source will be pretty much constant. You may need to recalibrate the machinery every 3 or 4 months or so, but during the daily operation this will be effectively constant. So to finish off, let's just have a look at the nuclear equation for this. So we've got strontium 90 goes to yttrium. We remember that in a beta particle emission we move one place up in the periodic table, and so plus a beta particle, which is a high energy electron, 0 mass, atomic number -1. And so you can see there that the nucleon numbers and the atomic numbers all add up.